All right, so continuing, excuse me, the third in a series of talks about plasma modeling of lunar magnetic anomalies. I'll be talking about a continuation of the same model we just heard from Shahab, now applied to the Reiner Gamma magnetic anomaly. And I know I advertised both Reiner Gamma and Airy, but that actually wouldn't fit in 15 minutes nicely. So I mostly focus here on Reiner Gamma. As we've heard, this is sort of the archetypical lunar swirl that everyone talks about. It's very well known. This picture is actually only showing the main portion of it. It actually has another tail that extends very far upward. But as you'll see in the talk, really the main head of it is what I'll be focusing on. And then really, in addition to trying to understand the electromagnetic type of interaction, which we've now heard about from a couple talks, the goal that I'm trying to get at is not only understanding the electromagnetic interaction, but also understanding how it is we can quantitatively or begin to quantitatively understand the surface weathering from the protons and try and relate this directly to the albedo features that we see. So just again, to beat this into everyone, the moon possesses diverse and scattered crustal magnetism. You see here on the left is electron reflectometry results from the lunar prospector spacecraft showing the surface crustal field strength, both in the mid-latitudes and at the polar regions. The red color for here down in the middle is the South Pole Aitken Basin, for example. And so you can see it's scattered both places with very little magnetism, places with strong crustal magnetism. Reiner Gamma at this scale resolution shows up as basically this tiny little orange dot right here. It's a very small crustal anomaly, although it's actually very strong. We do know that it has, from both Clementine and lunar reconnaissance orbiter images, it has this apparently unweathered, although somewhat complicated, albedo features on the surface. And again, the main sort of cartoon version of the electromagnetic interaction is that these crustal magnetic anomalies on the surface, they decelerate the incoming solar wind protons mainly through the formation of an electrostatic field. So the magnetic fields themselves are not really strong enough to decelerate the protons. The ion gyroradii are too large, but some amount of either Hall term or ambipolar or convective electric fields are able to really repel or slow down and possibly repel the incoming solar wind protons. But really a lot of the details that go on down below here, as we're hearing about in just the last few talks, are just only coming into light, so to speak. So focusing a little bit more specifically on Reiner Gamma, the Kurata et al. Paper that was referenced by Jan a couple talks ago had essentially simulated this entire region with a single dipole. And in fact, to some degree, that's all you can really do with observations quantitatively because of the limitations of how small Reiner Gamma is and the lunar prospector flyovers. But Doug Hemingway and Ian Garrick-Bethel back in 2012 proposed sort of an empirical or qualitative model for what you could possibly get for the source magnetization for Reiner Gamma. And they were reasonably clever about it. They said, well, if we take the solar wind shielding hypothesis as probably true, we can say that regions with brighter surface area should have more horizontal fields, because the horizontal fields are somewhat more effective at generating these electric fields which slow down the solar wind. And so they tried a couple different arrangements, but they arranged these little red dots are individual magnetic dipoles that are buried a couple of kilometers below the surface. And the paper goes into great length about how they fit this specific empirical model to the lunar prospector observations. It's consistent with LP at altitude. This sort of source inversion is inherently non-unique, but nevertheless, they can go ahead and use this model to try and look at what the magnetic morphology is here. Now, if you had magnetic eyes, this is what you would see at the surface. Under this model, you see sort of this wishbone shape. The red values are showing you the highest magnetic field strengths at the surface. And again, you get these narrow lanes that they appear to see in the magnetic field that presumably would allow the solar wind axis into the surface. And so the question that I'm working from, and I was inspired by their work and have been working with them the last year or so, is could we possibly take this arrangement that they've empirically proposed for Reiner Gamma, and could we feed it into the hybrid model? And could we try and sort of close the loop, so to speak, between proposing what the magnetic field should be, running that through a plasma model, looking at what the surface weathering fluxes are, and seeing if those surface weathering fluxes are consistent with what the solar wind shielding hypothesis would tell you, that these narrow dark lanes and these dark regions that are unmagnetized have full access to the solar wind, while the shielded area, or the bright areas in the albedo anomaly are relatively shielded. So that's essentially what we did. So we focus in a little bit more in the vein of congratulating LRO. I took this beautiful image that was very easy to capture from the LROC camera. That's a zoom in of the main head. And just to simplify the model a little bit for the hybrid application, this dashed rectangular box sort of shows the domain that I basically cut out of the lunar surface to run into the hybrid model. Now, the hybrid model is three-dimensional, so it models the altitude above this sort of rectangular region. But the reason I picked this is it shows some nice symmetrical features that are a little easier to interpret, namely these bright lobes as you cut across the main head, and then punctuated by these very dark lanes. And so if we could reproduce this qualitatively, this kind of a shape with the surface weathering, then we might be able to more understand and more validate the solar wind shielding hypothesis. So again, we took this model and we cut across and plugged that into the hybrid model. But there is some ambiguity in what we choose for the directions of the magnetic dipoles that are sitting under the surface. Now, Doug, Hemingway, and Ian, they proposed a model whereby, if I'm looking at this in cross-section, these are the magnetic field lines. Their two sets of dipoles were all oriented horizontal to the surface, and this was to try and get as much horizontal field strength as they could eke out of this model. And then we actually played with a lot of this. We had fun as modelers, and we changed a bunch of the parameters. And one of the other interesting cases we came up was the case where the magnetic geometry kind of had this perpendicular to the surface orientation, but with this anti-aligned geometry. And so you might think, if you look at these broad features, that the magnetic field topology looks very different, but in actuality, very close to the surface, it's qualitatively almost identical. What I'm showing here on the bottom is this lower trace across, and you can see this is for this case 1 that I'm calling, and this case 2. Both have qualitatively the same topology, sort of at an equivalent altitude that Lunar Prospector would be measuring. You see a peak in the magnetic field with roughly a single peak, followed by the sinusoidal in the red curve, that's the vertical field, and a single dominant component in the horizontal. This is actually very similar to what Lunar Prospector has observed in its continued flyovers over Reiner Gamma. So I'm going to try and compare these two cases side by side to try and understand a little bit of what changing this magnetic topology does to the system. So on to the results. This is for case 1. This is sort of the canonical, I call it the Hemingway and Garrick-Bethel model. I have my two dipoles oriented horizontal to the surface. The panels here show the magnetic field strength, the solar wind density, the electrostatic field strength, and then the proton energy distribution at the surface. So you can see these two lines of dipoles. They generate sort of these two large humps in the magnetic field where the magnetic field magnitude is concentrated. As the solar wind is coming down from the top, it's a little tough to see here in these colors, but there's a very slight density enhancement as basically the solar wind is slowing down as it approaches these anomalies. We can also see that that's basically affected through this electrostatic potential. So these potentials are on the order of 400 or so volts, very typical for what observations have suggested are present at these anomalies, and they're correlated right with the horizontal field strength from these buried lines of dipoles. We then turn to look at see what it's doing to the protons. The undisturbed solar wind outside of the anomaly region is showing here just under a keV in impact energy, but right when we get to over the dipoles, you see that they're very effective in reducing the proton speed and flux to the surface. And so we do really confirm the notion that these horizontal field strengths are actually fairly well capable of decelerating the protons locally right overhead, and maybe that's one way with getting these this differential weathering. Now, if we move from case 1 on to case 2, where I've reoriented the dipoles now to be sort of anti-aligned vertical, I again have the magnetic field, the proton density, the electrostatic field strength, and then the proton flux at the surface. We again see these two sort of lobes in the magnetic field. I have a somewhat stronger density enhancement. There's a little bit more complicated shape here. But what's really intriguing, actually, I found was the electrostatic potential. You can see instead of having these sort of two lobes in the electrostatic potential that we had in case 1, the fact that we vertically oriented these dipoles, when you put those next to each other, they tend to get horizontal fields in between them. And that's actually where we see the greatest strength in the electrostatic potential. It's actually a little bit off the chart. It's a little bit over 500 volts in magnitude. And that gives us a slightly different weathering pattern. We can see that directly over the dipole, since they're oriented vertically to the surface, the solar wind actually doesn't see any electrostatic field, and it directly impacts the surface. This is really reflected in this energy spectra right at the surface. We see the undisturbed solar wind far away from the anomaly. We see this outer band is sort of somewhat lighter outer lobes of electrostatic field cause some deceleration. The center lobe is causing a bunch of deceleration. There's essentially no solar wind beam any there. But right over the dipoles where these vertical fields are, we see this very narrow high flux penetration of solar wind plasma right down to the surface. And it's not only the plasma that originally came incident to that region, but it's actually the plasma that's sort of being diverted around this very large electrostatic potential in the middle, that's basically being funneled down and increasing the flux, so to speak, into these narrow channels. And now the question then becomes, how do we relate this flux to something like a surface albedo? And that's a little bit more qualitative. But what I can do is I can take the models, and for this case too I focus on, I look at the relative solar wind flux. So a unit of 1 in this is the undisturbed solar wind impacting the lunar surface. And as I approach these two sets of lines of dipoles in the model, you can see that the relative solar wind flux changes drastically. Just outside of the dipoles and in between, in this case too, you see a reduction in the relative solar wind proton flux. We got down to 30% or less of the solar wind in this case. But very strikingly, we get these very narrow, very high flux lanes, you might call them, that occur right over these vertically oriented dipoles. And you can qualitatively, again, go back to the LROC image and you can compare this to the optical albedo, and you can see these broad, bright regions, which perhaps, in a qualitative sense, correspond to the shielding that's occurring outside of these lanes. You see the inner region is shielded, it's bright in albedo. We see it's consistent that it's relatively shielded from the solar wind, but we are able to reproduce these remarkably narrow lanes in the swirl, so to speak, if these solar wind protons are really what's causing the weathering. So this was really encouraging. I think it's important to note that Ian and Doug, as more the geophysicists, had a lot of trouble scratching their head about how you would get a magnetized source that looked something like this. I think that's perfectly fair, and I think one of the takeaways is it's probably not exactly this, but we can begin to conclude that there must be some type of very strong vertical field that really goes to generating these narrow lanes. So again, just to point out these features, we see the broad lobe in the middle, for example, and these narrow lanes kind of qualitatively correspond to each other. So in summary, we're really able to getting to the point where these plasma simulations can close the loop, so to speak, and relate any given proposed source magnetization to the surface plasma flux and the weathering patterns. I definitely think we still need to understand the quantitative relation between how much solar wind flux and how bright of a surface. Obviously, it's a very complex question. We can see from the observational spectra that it's not as simple as just less weathering. There's many additional processes that are being folded in there. I'm encouraged that we can get these very sharp dark lanes. It's always been something of a mystery how you get something so incredibly narrow, so small with respect to the plasma lengths. But I also, and John Keller, I think, asked a prescient question, is if the solar wind shielding hypothesis is really going to be true, then as you play with all the various parameters that go into the solar wind, including the zenith angle, the IMF, and the solar wind plasma parameters, and even the different source magnetizations, that weathering pattern has to basically stay there essentially over geologic time. So I've shown, 0 solar zenith angle, a given sort of nominal solar wind plasma parameters, but there's a whole task to be done that we're just starting, where we start to push on the anomaly, so to speak, with different solar wind conditions, and look and see if we can preserve that surface weathering pattern that looks qualitatively like Reiner Gamma. So this is exciting work to continue in the future. So thank you.
Yeah, I have a couple probably stupid questions, but first of all, the regions where you see these sort of spikes in the solar wind flux, is that, I assume that that's solar wind protons and not necessarily electrons. That is to say, the electrons are going to not necessarily come into those regions. And the other question that I had was that when I look at this, you've got these thin lanes in which you essentially weather these regions around the swirls. But overall, if you look at the region, it's actually, you get less weathering overall. So I'm trying to reconcile that with what we heard from Amanda earlier on, where these swirls in general, when you look in the blue, appear to be more mature on average.
So both good questions. So to your first question, yes, this is proton weathering. This is the proton flux. The hybrid model treats the electrons as a fluid. So we don't kinetically track the electrons as if they were a PIC. The electrons will have a tough time getting into these cusps because of magnetic mirroring effects. But it's much more of a self-consistent problem to get at. As to your second question, I think if I understood it right, I'm not quite sure I understood how the whole thing is relatively shielded, but I do see that Amanda's results sort of suggest that it just doesn't quite look like plain unweathered regolith. There's an additional process. And I actually think Amanda hit it on the head when she said that it's micrometeorite bombarding. We're able to tease that piece out perhaps by looking at this blue spectrum. I will admit that the spectral analysis is far outside my area of expertise, so I can't comment on it much more than that. But I actually do think that these types of simulations combined with the optical measurements maybe allow us to tease out what role is solar wind and what role is micrometeorite bombardment.
Okay, quick question is that you show two scenarios of magnetic field orientation. So how many other possible scenarios there will be, and do you see the chance to use all this result to back out the surface field?
Yeah, so I actually have a library of about 50 of them where we went a little bit crazy. We didn't show the geophysicists, but we changed all the orientations. We changed the strength. We actually put like a third dipole under, and that was actually our first goal, was to see if we could find a unique solution that would help us, get the magnetic field topology. And I'm happy to show you some of those results, and it's kind of a zoo of different results. It's definitely a non-unique problem, though.